perhaps one point I should have said earlier on is that when I introduced this null cone, remember that these were d plus 2 dimensional coordinates. If instead I put -1 here, this would be ADS d plus 1 dimensional space. Both the null cone and this ADS space have isometry from it d plus 1, 1, assuming that I was dealing with a Euclidean space to begin with. This space has got d plus 1 dimensions because you can't impose the projective requirement because of the -1 on the right-hand side. But if you make the x's very large on ADS space, and x is very large effectively corresponds to the boundary of ADS space, then the boundary becomes the null cone, which is why a theory, gravitational theory on ADS d plus 1 dimensional space reduces to conformal field theory on the boundary. This is just the tip of the ADS CFT correspondence. Let's go back to what I'm doing here. So these conditions here define when we have a conformal transformation. Here I'm considering transformations where these are essentially arbitrary. So I consider transformations on the fields parameterized by some function of x, some omega and sigma, which which are of that form, but without any relationships between the b, the omega, and the sigma. And then the claim is that for a conformally invariant theory, the action constructed locally in terms of the fields, the result must be of this particular form. And so the point is that if we were to vary, so the point is that this transformation, we vary b, we will get the equation d mu t mu is equal to 0, because on the equations of motion, so this is on the equations of motion, this variation has to be 0 for any variation of the fields, and in particular for variations of the fields of the kind that I'm describing. So this is only true if we assume these, so T is constructed by the fields, and this equation must be valid if those fields satisfy the equations of motion, which obtain from varying action and requiring it to be stationary. But we also have conditions by varying omega, which is that T mu is equal to T alpha. mu. By the way, this x has to be antisymmetric in the mu and nu indices. And then finally, we would have that the trace a to mu nu, T mu. So this contribution we get by varying sigma. So of course, over on these contributions we have to integrate by parts, which introduces a minus sign. This is, if I've done the things correct, minus 2 d mu times x alpha mu mu. So I want to be able to define an energy momentum tensor for this particular theory. And now we've got one which is conserved, but which appears to be antisymmetric, and also appears to have non-zero trace. However, what we can do now is to define an improved energy momentum tensor. And this is equal to minus T alpha. So if I define this object, I choose these combinations in such a way. So this object now satisfies the following conditions. It's also conserved. It's now its antisymmetric part vanishes. And now its trace vanishes as well. So, sorry? So at the moment, x is defined by this assumption here, that the variation of the action, there has to be a contribution proportional to this, which involves t mu nu. The assumption is that the action is invariant if I restrict v, omega, and sigma to ones which will generate conformal transformations. So this is like, it's a version of Nordita's theorem, sort of slightly modified. Now, Nordita's theorem states that if you've got a variation under continuous symmetry, there will be a conserved current. Here, the conserved currents are going to be tied up with the energy momentum tensor, but I also want to fix up the energy momentum tensor in such a way that it satisfies the requirements that it's traceless, symmetric, and conserved. And so this quantity here is called an improvement. So normally if you could look in the sort of at least moderately old-fashioned field theory books and they define an energy momentum tensor, they do it, and then you usually have to fiddle around with it in such a way as to make it symmetric and conserved by introducing so-called improvement terms. This procedure essentially gives you that straight away. And in fact, I will now tend to call the energy momentum tensor T.
Can you quickly say why one wants to improve it?
Sorry?
Why does one even want to improve it?
Why is what?
Why does one want to improve it?
Well, you mean to make it symmetric and traceless? Well, it's nicer that way. I mean, probably. Well, of course, if you want to relate it to a theory which you obtain by varying the metric on a gravitational background, that will always be symmetric. I'll make a brief comment on that in a moment. Okay. Well, of course, if we have such an improved energy momentum tensor, then for any conformal killing vector, I can define a current. So remember, V is something which is quadratic in X, and this will satisfy so if I take its divergence, and then if I know that the energy momentum itself is divergence free, this will be equal to. Now, if it's symmetric, I can replace this by d nu v nu plus d nu v nu. And then if V satisfies the conformal killing equation. Sorry? Where? This is a V. It's meant to be Roman. Whereas mu and my mu's have a sort of slightly sharper point at the bottom. Okay. So V just labels the fact that it depends on this conformal killing rate. So this will be equal to 0 if V satisfies that equation. And so then we have a conserved current, and you can define charges, Q V, which is equal to the integral over some object. So that's the usual way in which you define charges, and these will become the generators of the conformal group. So I'm dealing with everything together all at one time. Now make a observation at this point. Supposing it were the case that the energy momentum tensor was not traceless. So I'm now going to go back from theta to t. So I will no longer make that distinction. But now let's suppose it was the case that d mu, t mu, is equal to d mu b. Supposing we had a theory in which the element tensor was not traceless but was equal to a divergence of a current, then it's not difficult to see that d mu, t mu, x nu is going to be equal to d. And I can define a scale current, J mu s, is equal to t mu x nu. Such a current is going to be divergenceless, and so this generates scale transformation. But in this particular case, if we just have a divergence of a current on the right-hand side here, but not zero, you would not have special conformal transformations, you would not have the full conformal group. However, if we could write that v mu is equal to d mu L, say, supposing this was equal to the divergence of the current, then we could do another modification, namely that theta mu mu is equal to t mu mu plus 1 over d minus 1 times d mu. You see, we want to preserve the fact that it's conserved. So that's a way in which you can introduce a engineering tensor by construction. This is now, it's symmetric, it's conserved, and it's traceless. Because if you take the trace of this, this will generate a d, there was a 1 there, and so cancel out the denominator, cancel that off. So there's a huge amount, well, quite a large amount of literature, especially in the last year or so, discussing the extent to which various assumptions that you can make on the theory that if this is true, that this is true. And therefore, you know, can you have theories which have scale invariance but not conformal invariance? In the case of unitary theories, it's almost certainly the case that you can't, though for sure you can construct non-unitary theories which have scale invariance but not conformal invariance. Now let me just make a comment about, suppose we were to consider a field theory on curved space. Suppose we have a theory S to phi, but now it depends on some metric g mu nu. So we now consider the theory on curved space. In this case, let's suppose we have a Weyl invariant here. So we have a theory here which is invariant under diffeomorphism, which means reparametrizing the coordinates, so that the theory we can consider delta v of g mu nu is equal to d mu v mu. So these are now covariant derivatives defined on the curved space, and then we have delta v of phi is equal to d delta phi plus other stuff. The other stuff is related to considering transformations on the various indices, or if they're fermions involving the Theophan and all that kind of stuff. So this is what you would have for any theory which was extended to curved space in such a way it was reparameterization dependent under transformations of the coordinates. And now let's suppose that we have a Weyl invariant. Weyl invariant means that you can consider transformations on the metric which involve scale transformations. violent variance was introduced by Weil around about 1920-21, where he gauged the symmetry and wanted to relate this to electromagnetism, which of course doesn't work, but nevertheless it led to the ideas of gauging variance and so on. And now, there's also going to be delta sigma on the fields, which I won't specify. Now the point is that if you have a Weil invariant theory on curved space, which is also invariant under diffeomorphisms, then if you restrict flat space, so the point is a theory which satisfies those conditions, which restricted to flat space, what you want is what is the symmetry group which is left? Well, the symmetry group which is left is one which leaves, so you want to consider G mu u go to 80 mu u, restricting things to flat space. But what subgroup of transformations are left which preserve that symmetry? Well, which preserve this friction, well then mainly these are things which satisfy so what I'm saying here is that any theory on curved space which is invariant under diffeomorphisms and also is Weil invariant, when you restrict it to flat space and you restrict the V's and the sigmas to satisfy this equation, it will be invariant. So such a theory defines a conformally invariant theory when you reduce to flat space. And of course, in such a theory, you can define the engine momentum tensor by varying it with respect to the metric. And note that in a general quantum field theory, for a general quantum field theory, typically you have an equation of the form for the trace in the energy momentum tensor. It's a sum over linear operators in the theory, or so normally have operators in the theory times their corresponding beta functions, plus potentially terms of the form ECC. Now, if you can argue that there are zeros of the beta functions, and also that these terms are absent or can be removed in various terms, so under RG flow, if it goes to a fixed point, where the betas are equal to 0 and the V mu is equal to 0, or possibly can be redefined away, you get a CFT. So this is a reason why, for instance, conformal field theories are relevant in the context of quantum field theory, namely that they're related to the fixed points under RG flow. Now the question of whether or not there exist non-trivial fixed points under RG flow is of course another question. Maybe in the past we tended to think that they were not present too often, but nowadays there's good evidence that many quantum field theories in 4 dimensions and in other dimensions do have fixed points at which conformal symmetry is present, and therefore you can use the technology and so on, which I will describe, in order to understand more about the physics of such theories. I want briefly to say something about Ward identities before moving on to the next topic. In the context of quantum field theory, actually, no, maybe I'll leave this topic and come back to it in due course. It's probably better if I discuss some other things first. So, yeah, let me go on to now to discuss now in more detail the action of the conformal transformations on field. So let's suppose we now go to a quantum field theory. You in which we have fields which are operators, and now we want to extend this to the conformal case. So we need to have a set of generators. Well, as always, so the generators of Lorentz transformations and also translations are meant to be standard. So always there's an angular momentum bit and there's a spin bit. So there are a set of generators S which obey the same algebra. So these are finite dimensional function matrices which you can work out in any particular case. And we then have P mu with finite vectors. D mu of finite vectors. That's all quite simple. And now we have to write down what are the additional commutation relations involving the generators of the conformal group. So B with finite vectors. So the point is that these fields now have not only a spin which determines what set of matrices you put there, it has a scale dimension delta which is defined in terms of the action of the dilatation operator on these fields. And then there's a slightly more complicated one involving K mu, which probably I'll write it down, but so this is something which involves terms which are quadratic in X. And then there's a bit which involves the spin. However, details of this will soon not be relevant. So this is the set of commutation relations involving the various generators of the conformal group, which extend those of the original Lorentz group and translations. However, in conformal field theories, you can make a correspondence between the fields and states. So what I want to do is to consider how the operators act on states. So let's consider that any field, I define a state by considering the action of the field on the vacuum state at the point x equals to 0. It doesn't have to be x equals 0, you can choose any other point you like, but you choose a specific point in such a way that this defines a state. And now, on these states, things simplify a lot, because the eigenvalue of D is just delta. So all the terms involving x drop out. K mu on this state is 0. You have to worry a little bit here because K involves derivatives, but remember the terms involving derivatives get multiplied by 2 powers of x. And so if we have 2 powers of x, and then mu nu on by I is equal to pi mu. state which satisfies this set of conditions is called a conformal primary. So this is a conformal primary.
First one question, so this phi is not allowed to be gauged
Right now it's not a gauge.
but it still has it's massless and has a spin.
Well, it has well, it will be massless because, of course, these transformations preclude the possibility of there being a mass. But, well, we can, of course, extend this to gauge fields, but I'm assuming that at the moment I'm looking in the sector, I'm looking at all the gauge singlet sector.
Does it really make sense to, I mean, your index I, would you use spin 1 or this way?
Well, it may be spin you like.
Density 1.
What?
So it would be density 1.
In principle, yeah. I mean, I think, well, maybe this might become clearer. I mean, I'm assuming that any, so this index here defines finite dimensional representations of OP minus 1, or OP. The finite, I mean, they're not unitary, of course. So the rotation group, the representations here are obtained from representations of here by putting in appropriate factors of I. But there's no assumption, I've not said anything about whether these things are unitary or not at the moment. So everything, this is something which I'll come to. The fact is that for this particular state, P mu doesn't respect the condition that x is equal to 0. And in fact, all the states are obtained by acting on this state with arbitrary many p's. Well, the index, so each of these p mu's can have arbitrarily many powers. So I can construct a representation of the whole conformal algebra in terms of these states just by starting, so this is a bit like starting in angular momentum theory where you start Jj and then which satisfy J plus on this is equal to 0, and all the states you get are given by J minus Tn. So here we start from a state which satisfies the conditions which are it's annihilated by K. It has an eigenvalue delta for the dilatation operator D. It belongs to a finite dimensional spin representation under the action of M. And then we generate all the states of the theory by acting on this state with arbitrarily many p's. Now, unlike the case of rotations where this J minus stops after a certain time, in fact, when you, after 2J plus 1 steps, this stops and you get 0, these applications of these p's don't stop. I mean, I'll describe some conditions in due course. So we have an infinite dimensional space. So at the moment, I've not imposed any conditions connected with the theory, with this representation being unitary or otherwise. So this is just a representation which I construct from this. But note that all these states will have eigenvalues under D of the form delta plus n. Every time you act on this state with a p, you increase the eigenvalue of delta by 1. So these are a representation in which the eigenvalues of delta have a minimum value, they have no maximum value. Now, for the conformal group, there are various ways to construct representations. These would typically be called highest weight representations because they have a lower bound. Actually, it should be called lowest weight representations, but nonetheless, delta has a lower bound and then it increases without limit, depending on the number of p's you act on. All right, so I need now to try and discuss the extent to which we can have unitarity in the field. So this, if you like, defines a set of Keck vectors in the theory, and I want to define some associated bra vectors with which I can have a scalar field. So let me remember that for any phi I of x, there is a conjugate phi bar I. The point is about these spin representations that you have in general, in their fermions, for instance, when we take the conjugate, we have a different spin representation. So I want to define, in terms of this, a field, let's call it phi tilde, which is going to be of x, which is x squared minus delta times phi. So here I do an inversion. And I multiply it by the appropriate inversion matrix. And I also scale it by an amount x squared to some power delta which is appropriate to this particular field. Now, if you work it out, and again, this is an exercise if you want to do it, namely that P nu with phi tilde of x is going to be equal to x squared. So the point is, because of this inversion in here, we'll get some dependence. Minus 2. Well, I'm assuming this is, sorry, this, I've done this here for the scalar case because that's easier to work out. And then d tilde, d is equal to minus x plus okay, so I've restricted the case where phi doesn't have any indices, but the point is that you can see that phi tilde looks like it transforms pretty much as phi transforms, except that where this involved k, and there's also a d here, so there's a minus sign in this. And then the point is that if you work it out with k nu with phi tilde of x, minus p nu. So the point is I do this through the inversion operation, I define a field which appears to transform in a very similar fashion to the original phi.
So can I ask a question? The commutation with p, is it supposed to be phi tilde or phi on the right?
Oh, it should have been phi tilde, I'm sorry. Anyway, so the point here is that I can then define a conjugate state, phi tilde of I, to be equal to so note that this is a Satsu at the point x equal to 0, but really it's the point of infinity in terms of the original field, because putting x equal to 0 here. And you can see But in a rather analogous way, what I considered before, we have that, for instance, the phi tilde of I on EU is equal to 0, and the phi tilde of D is equal to delta on phi tilde. I won't write down the commutation relations involving M because they're rather similar. And so we can then define a scalar product which is related to that for the two-point function, named the phi tilde by j is equal to delta j. Sure. Well, I'm assuming delta is real at the moment. Okay. In fact, it will have to be real in just a second, because if I chose it to be otherwise. The point is that with this scalar product, we have that k mu dagger is equal to p mu. D dagger is equal to d. That forces the eigenvalues of d to be real. I mean, you want there to be delta bar there. Yeah. Yeah. Well, the point is, let's suppose.
Not complicating in the sense of complex, but just to say it's the complete dimension.
Well, I mean, when I take the original field phi I, the scale dimension delta, if delta were complex, and I wanted to, sorry, this originally had it dipped down. So there's a essentially complex conjugation that takes you from this. So this, if delta were complex, that would be the complex conjugate field there. And then there would be the complex conjugate scale dimension there. But in this scalar product, because I mean, I'm effectively assuming that D dagger is equal to D, K mu dagger is equal to P, and also M mu dagger. So this procedure is essentially consistent if the delta is only if the delta is real. So I'm, yeah?
This is forbidden now from the principle of quantum field theory, and this the emission of mu should be emission operator.
Well, that's where the slight subtlety. I mean, I've defined. I mean, when you say something is Hermitian, it's always relative to a particular scalar product. The scalar product I'm defining here is in terms. I mean, this of the fields acting on the vacuum state. I mean, if the problem is that if you go back to the original, so the standard assumptions in quantum field theory, the way I've defined things, is that P mu dagger is equal to and K mu dagger.
And we have a Hilbert space, so the scalar product is already given.
Well, not necessarily. I've defined the scalar product in terms of the two-point function of. So this comes about from the fact that I've chosen phi bar I event, phi j phi, to be equal to I j. There's no God-given notion of Hermitian conjugate of an operator. It's dependent on the scalar product that you choose to define in the theory. So I've started from a set of operators acting on states, the vacuum state plus the states formed by the fields acting on that vacuum. And within that framework, I define the scalar product effectively here. which flows from the fact that this two-point function. The problem is that if I stuck with the original notion of the scalar product, what I would then be considering supposing I considered this state, phi, to be phi of 0, acting on this vacuum, and then I wanted to consider this. This is equal to infinity. Well, the thing is that I've chosen a scalar product which is finite by this way of constructing things. I mean, if you like, I'm using radial quantization. It's another way of saying that. Namely, that I'm considering the states. So the point is that this state is defined in terms of the action of the field at the origin. This state is determined in terms of the action of the field on the corresponding bra vector at infinity. And with this way in which I've defined these things, so the point is I've done a mapping from the original phi to this object here through the inversion tensor. And then I've defined the scalar product in terms of, so this is a set of vectors which are dual to the original set of things, which have a finite scalar product. And this is the appropriate way of defining a Hermitian conjugate with respect to this particular scalar product. So in your original theory, if you restrict to the obvious definitions, then you'll get a scalar product which is infinite for the fields. But I want to consider scalar product in terms of states defined in terms of fields acting on the vacuum. And these are not, so this is not a normalizable state, whereas in this context, I've defined something which is normalizable. You disagree? It's a matter of choice. I'm making choices here. There's nothing wrong with the standard choice, but it's not particularly
useful. It might be, and one thing, it might be a little hard to recover the Minkowski quantum field theory physics.
Well, I mean, I think you can construct within this framework a set of, I mean, I agree that I'm probably presupposing the Euclidean version of the theory at this point. But once, if I knew all possible states within the theory, I can define correlation functions, and if those correlation functions satisfy certain conditions, I can continue them back to Minkowski space theory. Well, in any theory, you know, the so-called Osterwalder-Schrader axioms, if they satisfy those conditions, I can continue them back to Minkowski. I mean, I've not said anything here about whether this is free or not. I've just constructed a set of states which formed by operators acting on the vacuum state, and also defined a dual space. Right. So here we have an original space D. I have to define a dual space. I define a scalar product of them, and there's a one-to-one correspondence between the space and its dual. Right. So we have what amounts to a Hilbert space, okay, on which there are certain hermeticity requirements, namely that these are the things. There are other ways of looking at this, but nevertheless, the point is that when you define the group, let's say OD, 2, the proper mathematical way of doing this looks for the maximal compact subalgebra, which is OD cross O2. And then to look at representations of this and extend it to the non-compact case. What I'm doing here is equivalent to doing that in a slightly more way which is motivated to physics, in my opinion. Okay, so what I want to discuss now is some of the consequences of these things being unitary at this basis. So, assuming, so what are the requirements that you get assuming these conditions? And we'll find some constraints on possible scale dimensions of everything that the field. Well, let's consider, for instance, let's consider a scalar field. I mean, a scalar state. So there are no indices here. And that we're in the Euclidean regime. Now let's assume that mu therefore on phi is 0. And let's form the scalar product phi half mu. Now we have that k mu with mu, in my convention is 2 mu. That's h. And we also have that k mu on phi is equal to 0. And note that this has to be greater than or equal to 0 if k mu is the Hermitian conjugate of P. I believe it's greater than or equal to 0 as a matrix. And now, of course, we commute it through, and this is 2 delta mu times delta, because we can use the eigenvalue of d on this state given mu delta times. And so we must have the delta is greater than or equal to 0. Well, it's a rather trivial consequence. In fact, it can only be equal to 0 if P nu of this state is 0. So actually, in that case, the state is just a vacuum state. Now, to get something a little less trivial, let's consider what happens when we have 2 P's. So let's consider the condition that we get where we have phi bar k mu p sigma and rho. Again, this is something which should be positive. Now, one has to go through a little bit of algebra to work out what the result is going to be. When you commute k with p here, so you want to, I'm sorry. So you want to commute these two. So you want to move the k's to the right where they hit the state and you get 0. So this is a bit like playing with creation and annihilation operators. Now let me short circuit the calculation. It's just an exercise in using the commutation relations. And so the whole thing must be symmetric in sigma and rho and k and mu. And then minus mu. And as a matrix, this has to be positive. Now, if you just contract this with delta mu nu, let's contract with delta mu nu, you will get that basically 2 delta plus 1 minus d is greater than 0. So I mean, what you need to do is to work out all the eigenvalues of that matrix and then check that they're all positive, or what conditions are necessary for them to be positive.
Can I ask a question?
Sure.
So how is the inner product of the phi bar with phi in this new one? What do you mean tilde?
Sorry, how is this?
How is this inner product defined?
Well, it's defined by essentially this condition here. It's equal to 1.
Yeah, so how does it become for phi bar? Is it non-zero or is it?
Oh, I should
finite?
imply tilde, perhaps. In my notation, I'm sort of being... The point is that I have a correspondence between a state phi and its conjugate such that having the k on the phi's is 0 and the phi tilde is e. So the idea is I need to move the k's to the right, the p's to the left, and I pick up various commutators, so I know the algebra of the group, and I know how the m's and the d's act on the states. So this particular, so in some terms, this comes from D, and these terms come from S. And the consequence of all this is that we have this inequality, or that delta is greater or equal to d over 2 minus 1. So this is a constraint on the scale dimensions of spinless scalar fields, or the states corresponding to them. Note that if we have equals, the only way this can happen is that p squared on phi is 0. Or if you translate back to, so this is going to be del squared on phi, 0. So that just corresponds to a free massless scalar field, which is then the state which has the lowest possible eigenvalue for delta in general dimension. Let me do one other example, but one involving the state of spin. So at the moment I'm discussing things with a Euclidean signature. So let's now consider a state V rho which has a d-dimensional index. Now we need to know that we need to suppose that d on V rho has eigenvalue delta. Right? We also need to know how mu u acts on V rho. Well, in this particular case, it's going to be equal to delta mu rho, which is sigma minus delta mu, delta mu rho. So this should. So this is effectively defines everything about this state. The first one tells me what its scale dimension is. This one effectively confirms the fact that this is a d-dimensional vector field. Now let's consider what happens if we work out the scalar product of the following form, namely that V sigma. So in this case, we have a scalar product. This is equal to delta sigma rho. There is no distinction between. So this is a real representation, so we don't have to worry about issues of the conjugate spin representation. And then V sigma K mu, P mu, big rho. So again, it's just a question of using the commutation relations of K with P when K hits the state V on the right. So we have that K on this is 0. And we just do the commutator. And this is going to be equal to delta mu nu, delta sigma rho, d. So this is when we use the delta, and then plus the term involving the spin. So this comes from the matrix F. So this has to be positive as a matrix. Now you want to find basically the eigenvector corresponding to the lowest eigenvalue of this. So if we contract this with delta nu rho, we will get delta plus 1 minus d greater than or equal to 0. So this is the condition that's necessary on the scale dimension of this state for this to be part of a unitary representation whose states have positive norm. So,
sorry, how you say something just how you look for a unitary representation?
well, I mean, looking for a representation of which the hermeticity properties are respected, because I'm assuming that K mu dagger, well, P mu dagger is equal to K mu, this object here has to be positive.
But you agree that this doesn't lead to unitary representation?
Well, if I construct a representation which the hermeticity properties of the generators are respected, then that defines a unitary representation of the group. I mean, in order to if you have an algebra of which the generators are supposed to be Hermitian, and you can find the representation space on which the matrices corresponding to those generators are Hermitian, you then have a unitary representation.
Yeah, but I mean, if you exponentiate those,
well, I will if I exponentiate these generators and the states of the theory of the ones for which the Hermitian scalar product exists, it's sufficient. I mean, when you want to construct unitary representations of the rotation group, it's sufficient to find emission representations of the generators. And then you exponentiate. So,
how do you do that?
well, I mean, I can define, I have an infinite dimensional space formed by the action of all the p's on this. So the point is, what you need to be able to show is that the norms, so for any phi reflecting spin, the space of states that you consider, sort of V phi, is a basis of this space of products of arbitrary measures. This is a basis for that. If the scalar product of all states in the basis is positive, then I have a unitary representation. I mean, I can act on this basis with all the k's and all the operators in such a way as to define the algebra. So there are two aspects of constructing a unitary representation. You find a space on which the generators of the group are realized as appropriate operators. And you also have a scalar product on that space, which is with respect to which these operators are Hermitian and which has positive norm. That's my understanding of how it works.
I thought the unitary representation was where I can actually write down the unitary operator.
Well, I mean, look. Well, maybe we're. If you got if J dagger equals to J, e to the I theta n delta. Yeah. Is unity. Do we agree? And so here I construct emission operators, which I presume, well, look, there are technicalities involved in exponentiating, but nevertheless, this is what I'm doing here. Anyway, so we have this greater than or equal to 0. Under what situations is this equal to 0? Namely, if delta is equal to d minus 1, this implies that p rho is equal to 0, or that d rho is equal to 0. This is a conserved current. So the lower bound for the deltas corresponds to the conserved current. In fact, you can generalize this. At the moment I'm doing this in arbitrarily many dimensions. But if we generalize this, for instance, to a symmetric traceless thing with L indices, supposing this is symmetric and traceless, it's just a little exercise to show that this extends to delta greater than or equal to L plus d minus 2. So note that the previous case that I've just considered is L is equal to 1. So this and if this is equality, then this is a conserved higher spin current. Okay, so the point is that in a unitary theory, we're constructing a particular kind of unitary representation. These are unitary highest weight, possibly lowest weight representations of the conformal group. Namely, they're representations in which the value of the scale dimension delta has a lower bound. Now, this is not all possible unitary representations of the conformal group. There are representations of the conformal group where delta takes imaginary values. But within the framework of what I've described, if I want to find a representation in which delta takes real values with a lower bound, then these are the appropriate representations. I consider representation with delta is greater than or equal to delta naught, some delta naught, and that delta is real. And within this framework, suitably generalized somewhat, this forms a complete set of representations of this group. Okay. Well, there's, again, I guess 5 minutes left. What I want to do next, and we'll obviously have to go to the next lecture, is I've discussed, see, everything here is built on the fact that I understood the 2-point functions of the theory. So the point is that the 2-point functions essentially define the scalar product. And I use that to define the states of the theory in terms of the action of the fields at the origin and their conjugate states in terms of the action of the fields at infinity. But of course, any field theory, there's more to it than just knowing the functions involving fields at 2 points. We want to be able to discuss things at higher number of points. Now, I'll just set the groundwork for this. For simplicity, I'm going to consider scalar fields here, and I'll make some comment about the higher spin later on. So basically, let's suppose we have a bunch of scalar fields. Fine. And let's suppose that they have scale dimensions delta. And then we can write down what the two-point function so the point is that this is an object which is defined by its conformal transformation properties, namely that it acts as a field with scale dimension delta I at xi, and also a field delta j at this point. Well, this is equal to 0 if delta I is not equal to delta j. In a sense, that's sort of built into the formalism of what I'm doing here. It's a direct consequence of the transformations properties that I've been writing down. And in fact, if you choose this to be suitably a basis, you can write this as 1 over xij squared delta I times delta. In this framework, the normalization of the fields is sort of arbitrary, so it's always more or less convenient to define the normalization in terms of just making this equal to 1, the coefficient equal to 1. You can put in some arbitrary coefficient here, but then that will contain no real information. Now, we want to be able to consider functions involving arbitrarily many such fields. So in some sense, the theory is defined by if you knew phi, let's say, 1 of x1 up to phi n of xn, this would essentially tell you everything about the theory. For arbitrary n, well, plus if you generalize this to fields with spin. So at the moment I'm suppressing spin down the ground of simplicity. So I now want to discuss what happens when n is equal to 3. Now the point about this is that the conformal group maps any 3 points to any other 3 points. So in some sense, in the case of 3 points, the dependence of all this on x is more or less finished. Okay, now I'll fill out the details of that next time, but I think this is what I want to go next. So we want to be able to discuss this for n equal to 3, and then in due course for n equal to 4 points where further constraints